I'm an undergraduate student from Monash, and this summer holiday I was reading a statistical textbook, and today I want to show you what I learned. So let's open a text editor. It's called Atom. Let's create a Python file and plot some numbers. So these are our observations, these are the uncertainties, and we call this function to plot it. So I'll press F9 to run this Python file. I use Atom build extension. So it created the plot here. So here you can see sodium abundances of stars in a globular cluster. So each individual marker is a star. And you can kind of see that there are two groups, and our hypothesis is there are two populations of stars here. And what we want to calculate is the ratio of stars that belong to this second population. And we can quantify it with parameter r, which we found to be 0.7. So how do we calculate this number? We calculate it by looking at the bottom plot, and we find this minimal value in the middle, and we just plot the line through it, and then count the number of markers to the right from this line, and then divide by the total number of markers. That's how we find this 0.7. So it means 70% of stars belong to this second subpopulation. But wouldn't it be nice to calculate the uncertainty of this number? Imagine. So that's why I spent 2 months reading the textbook, and I learned how to do it, and the value is 0.1. So I want to show how to do it. So what we want to do is to build a statistical model, and we'll make a simpler one with just one population instead of two. So we'll say that sodium abundances are normally distributed, and standard deviation is 1, and the average is unknown, is what we want to find. So we don't know where this bell curve is, and more importantly, we want to find the uncertainty of this mu value. That's the whole point. So let's do this. Let's create a new file called model.stan and write the model in the Stan language. First thing you do is you describe the observed variables. The first variable is the number of measurements. Second variable y is the array containing the measurements. Then we describe the unobserved variables, that variables that we want to find. So we have just one unobserved variable, mu. Write it here. And finally, we describe the model. And Stan uses standard statistical notation. So this means that random variable y tilde means is distributed normally with average mu and standard deviation 1. Great. Let's run this model. So we create an instance of this class, and let's include this. And let's run it. So we're using cmd-stanpy library, and what it does, it runs stan, and first thing it does, it compiles our stan model from the Stan language into C++. You see this model HPP file? That's the C++ version of our model. And if you scroll down, you can see why we're using Stan language and not C++. And then it compiles this C++ model into an executable, here, the model. And we can just call this executable from a terminal, or alternatively, we'll call it from Python. Like that. So we call the sample method, then supply the data to the model, which are our observations and the number of them, and the current directory where we want to create the output. So let's run it. Press F9 again. So it created these CSV files here. Let's look at one of them. So it contains some comments unknowingly. Let's remove them because Excel won't like it. And let's open this CSV file. We'll hide some columns we don't need. Make it bigger. I'll move this column to the right. So it contains the column for mu, our parameter. Let's plot it. Let's make a histogram. And you can see at the bottom, if you select a column, Excel shows the average. So that's the value that we calculated for our parameter mu. So it's 0 minus 0.8. And then uncertainty, you can see from this histogram, it's about 0.2. Great. We calculate our parameter mu. Now, how are those numbers here generated and what do they mean? So the first number for the parameter mu is generated completely randomly by Stan, and then it calculates this LP underscore number. So this number LP means log probability. So I'll show you what it is. Let's look at our plot. So first we picked minus 0.6 for mu. This means this curve is somewhere here, so we moved it to minus 0.6. And then it calculates the log probability. That's the probability of the data given the value of parameter mu. So we calculate the probability density of all the data points. So I remind you the peak of the normal curve for standard deviation 1, the probability density of it is about 0.4. So for example, the probability density of this observation is 0.4. Probability density of this observation is much smaller, it's about, let's say, 0.1, and etc. So we multiply the probability density of all our data points, and then we take a log of it. So that's how we calculate this log probability value. So again, this is the probability of our observation given the value of parameter, given this value minus 0.6. Now, this minus 0.6 is calculated randomly, but how are other values of mu calculated? How does Stan pick other values for mu? And I'll show you how, because I think it's kind of cool. So let's plot log probability versus mu and invert the y-axis. So the y-axis is the log probability inverted, and the x-axis is our mu, value of mu parameter. So what Stan does, it runs physical simulation. It rolls the ball along the slope of log probability. So we start with the minus, for the mu with the minus 6.4 about here, and we write down its value. Then we flick the ball in with a random velocity. Let's say we flicked it to the right. So it rolls here, it's too steep, it rolls back a bit. And then after a fixed number of iterations, we record where it ended up, so this value. Then we flicked it in random velocity, let's say to the left. So let's say it's ended up here. So we continue flicking the ball with random velocities and just write down where it ends up. And we'll end up with most of the values for mu concentrated in this region of higher probability, and that's exactly what we want, because our distribution of mu should correspond to the probabilities of these values. Isn't it cool? So finally, let's take into account the measurement uncertainties. So each marker here is observed value, but it has some true value which we don't know. So let's take into account the measurement uncertainties in our model. So let's go to the model. Let's add the uncertainties as the known variable, and let's add y true, the true values of each data point as an unknown variable, and then we say that these true values are distributed normally around this mu value, and then that y, our observed value, is distributed normally around the true value with standard deviation equal to the uncertainty of this observation. So that's how we can use uncertainties of observations in our model. Cool, that is all, and you can find all the code from this demo and the link to the textbook that I mentioned at this address. Thank you very much.